Hello, hello everyone. We today we'll discuss the uh, part third of quantum mechanics and application. This application of Schrodinger equations. In part one and part two, we have discussed about the uh, difference between classical physics with the quantum physics and then the de Broglie wave concept, wave particle duality, Heisenberg uncertainty principles, and today we'll be discuss about the applications of Schrodinger equation. So before going to the application, let us focus on basically in classical physics we could predict the motion of planet and projectiles with remarkable accuracy using Newton's law. But when we zoom into atomic and subatomic level, where the electron, protons, and atoms behave in a way that defy classical intuition, we need a different set of rules. This is where quantum physics or quantum mechanics come in, and at the heart of this lies one of the most important equation one of important equations that describes the complete behavior of particle at quantum level is the Schrodinger equation. So basically Schrodinger equation developed by Erwin Schrodinger in 1926. The equation provides a mathematical framework to describe how quantum systems involve, much like Newton's law, describe the motion of macroscopic object. The Schrodinger equation describes the uh, behavior of particle at quantum level, but at this but this equation is not a just equation. It is a very powerful real world application that span across chemistry, physics, material sciences, and engineering. It allows us to predict energy levels in molecules, atomic and molecular levels, understand chemical bonding and reactions, model electron behavior in semiconductor and nanomaterials, and even explain phenomena like quantum tunneling, which power a device like tunnel diodes and help stars fuse hydrogen. So in today's lecture, we'll explore the Schrodinger equations application. Schrodinger equation is applied to different systems ranging from simple particle in a box to potential in step. We'll be discussing on only one dimensional. By examining these cases, we'll see how this equation shapes our understanding of microscopic world and underpins such of modern technology. So we'll be discussing in particular two applications. One is particle in a box. So this one of fundamental and illuminating problem in quantum mechanics is a particle in a box. Also it's known as infinite square wave potential. This simple model considered a particle like an electron confined to a one-dimensional region of space between two impenetrable walls. Outside this region, the potential energy is infinite, meaning particle cannot exist there. Inside, the potential is zero and the particle is free to move around the box. Although highly idealized, this model provides deep insight into quantum world. It was one of the first system where physicists observed key quantum principles like energy quantization, wave function behavior, and probability distribution. So we'll be discuss the particle in a box, its normalized wave functions, its expectation value of momentum, positions, and the probability of the particle location where can probability of the particle can stay inside the boxes, and also you'll have an idea about the discrete energy level and its position standing in a standing wave. These models also serve as a stepping stone to more complex systems and is widely applicable in understanding real world quantum system like electrons in quantum dots, nanowaves, even vibrating molecules. So as we develop our understanding on this model, we'll also briefly introduce about another quantum systems, that is potential step. The scenario involves the sudden change in potential energy, helping us exploring quantum phenomenon that defies classical intuition, quantum tunneling, and partial reflection of particle even when they have enough energy to classify across the step. So in this lecture we will be explain the key concept of quantum mechanical modeling related to wave particle duality, quantized energy and wave function. So basically the quantum mechanical model consists with the three major part or component: wave particle duality, quantized energy and wave function. So first, wave particle duality, as we know, that it is an idea that particle like electron and proton exhibit both even particle and wave-like property depending on how we observe them. So if we go back to historical context, that in 18th century 1801 the Thomas Young double slit experiment first shown the light behaves like a wave. Later on in 1905 famous scientist Einstein explained the photoelectric effect, showing that light behaves like a particle or photon. There we can find that photon is nothing but a quanta of light is nothing but a quanta of photon. And in 1924 that de Broglie proposed the matter particle like electron also have wave like properties, and we have discussed in our this quantum mechanics and application first and second part of the lecture about details in de Broglie wavelength. We know de Broglie wavelength lambda is basically lambda is defined de Broglie wavelength, and it is nothing but the lambda is equal to uh, h, h divided by p. So if we brief it, that wave particle duality basically describe in a box exhibit wave particle duality, meaning it behaves as both a wave and a particle. This is a key principle in quantum mechanics. And next, it the quantized energy. Basically in a quantum system, that particle can only occupy some an energy level which are discrete. They cannot just have a arbitrary energy. So in but we if we see that classical physics concept, that in classical physics particularly, or classical physics actually, the classical particle can have an energy depending on how much force is applied. But in quantum mechanics, a confined particle can only have specified energy directed by the system constant, like boundary condition can be applied or potential is applied. So example like particle in a box, which will be discuss in broad in this session, that so energy we'll see that in this session, that the energy En, that is proportional to basically n square, that n square is the n is the integer of the, it is define the different state. So we'll be explore this in a particle in a box, and also it can be observed in hydrogen atoms. And so basically this leads the discrete spectral line like those seen in the atomic emission spectra. And third part is the wave function. So basically wave function is nothing but a mathematical function typically denoted by this wave function. We already seen that it is basically denoted by psi. It is denoted by psi, and it's also function of positions and time t, and it describes the quantum state of a particle of a system. So the wave function describes and says about the probability of finding the particle at a given location. So wave function has some specific and unique features, or we can say the properties, like it must be continuous and single valued. We have discussed this in details. It must be normalized. That is, the total probability of finding a particle must be 1, and solution of the wave function is actually will get the solution of the Schrodinger equation. So in short, basically wave function gives us or tells us that where a particle is likely to be, or exactly where it is, and can see or can show the interference nodes and standing waves depending on the system. So we'll together this wave particle duality, quantized energy, and wave function basically together consisting the quantum mechanical modeling that uses this principle to solve the Schrodinger equations for different systems like atoms, molecules, or solid. The solution provide us basically that allowed energies, wave functions, that is probabilities distribution, and predicts about the physical behavior like bonding, spectra, or conductivity. So now we'll explore that details about the energy levels and the wave function. So basically, energy levels and wave function, if we define in stepwise, that we can frame as that first is ground state, second is the excited state, third is the energy quantization, and fourth is the wave function shape. So what is energy level? Basically, first energy level is nothing but the specific amount of energy of a particle can have, and we know the wave function is the mathematical functions that describes the probability of where the particle is likely to be. And so ground state are those lowest energy level corresponding to the simplest wave function, and excited state are higher energy levels who are characterized by more complex wave function. Next is the energy quantization. We know that energy is not continuous in quantum concept. It comes in discrete packet called the quantized energy levels. So what cause quantized energy? Basically, quantization arises because particles like electron are often confined, that is in an atom or in a potential oil, and the boundary condition of the system only allow certain waves like solution. So particles cannot have just like any energy. It must be one of specific value. So will we find out that energy of the ground state and upper state of particle in a box, and wave function shape. Wave function, we said that it is just mathematical representation or description of the function. So wave function usually written as psi, and mathematical function that contain all information about the particle state. So basically, in the square of the wave function gives us the probability density, that we know that we psi square, basically mod of psi square. So this is basically mod of psi square, and this will be give the information about that particle state. So before going to the particle in a box, if we want to discuss and to solve the one dimensional problem, so we must satisfy this, that one dimensional Schrodinger equation, define their potential energy or potential barrier V, solve the Schrodinger equation, define the wave functions, and solve for the allowed energies. So why these are matter? Because in atom energy level explain electron cells and the periodic table, In molecule, they explain bonding, vibration modes, and spectroscopy. In device, they govern the behavior of semiconductor, laser, and quantum dots. So basically, if we summarized that what we got here, now we will discuss the particle in a box. So basically the particle in a box, we are considering the infinite square wave potential. So basically this is the particle can move in this box, in the box freely, and we have considered only one direction, that is at x-axis, and we can see here this potential, potential, this boundaries that one dimension box, that is x is equal to 0 to L, and the potential Vx, basically here this x is basically is equal to 0 to L. It is 0, and it is varies 0 to basically L, and this potential Vx is 0, while this Vx is this V this Vx basically is equal to 0, while this x value is 0 to this basically is 0 to L, 0 to L, and this Vx is equal to infinity, while it is that greater than x is less equal, where x is less equal 0, and x is greater equal 0. That means out of this length 0 to L, this V potential is infinity. And so we know that here we can solve that one dimensional Schrodinger equations, and we can find out the solution of Schrodinger equation. So we know the particle here in the box is basically is used or defined to find out the physical setup and assumption of the model solving the Schrodinger equation for this system, the resulting energy levels and the wave function, and what this result tell us about the quantum behavior. So basically in this model it introduced the key quantum concept: energy, quantization, wave function, and the probability distribution. It provides a foundation for understanding more complex systems like atom, molecules, and nanostructure. It is applicable to the real world technology such as quantum dots, nanowaves, and semiconductor. So using these concepts, let us will solve that Schrodinger time independent equations, and next will be find out the wave functions of this system. So basically we have that our solution psi is equal to a sine of kx plus b cos of kx. So first, if we apply the condition at psi is equal to 0, at x equal to 0, then we can get the b is equal to 0. And if we apply the another condition psi is equal to 0 at x equal to L, so we can get 0 from this equation. Let's say this equation is 1, that we can get from equation 1 0 is equal to a sine kl. Or since a is not equal to 0, then we can find that since a is not equal to 0, then we can write at kl is equal to n pi, where this n is basically a integer number, and we can write this k is equal to n pi divided by L. So now we can write that psi value, that so we can write here the psi in general from psi n x is equal to, we can write a sine n pi x divided by L. So this is our general solution for this particle in a box, the general wave function psi. So the energy of the particle, we can write that energy of the particle En is equal to k square h square divided by 8 pi square m, or we can write it like h square n square phi square divided by L square 8 pi square m. So we just freshly write, we can write that En is equal to n square h square divided by 8 ml square. So basically in this potential in one dimensional box, the wave function is not that complicated, because here we are considering the only one dimension. So basically if now we want to find out that wave function in different its energy values in different energy level, we can find out from here. So now that for this n value, this particular this n value, there is an energy level, and corresponding wave function is given by by the equation of this, that psi n x is equal to a sine n pi x by L. So from here we can find out the psi 1, psi 2, psi 3 corresponding that energy level. Using this equation we can find out, and n value will be correspondingly 1, 2, 3, 4, and each value of En is the eigenvalue. So each value of En, this is the eigenvalue, and the corresponding psi n, this is basically the nothing but the eigen function. So now thus inside the box, the particle can only have discrete energy values specified by this En equation. Using this, let's say this is equation 3. So with this equation, one can find out the discrete energy values in particular levels. So also we here the important note is the particle cannot have zero energy. When it will be 0, then n is equal to actually 0, so there will be no state like n equal to 0. So now let us find out that wave function, and we know that from wave function properties that it is wave function has a properties of normalization. So if we want to find out the particle wave function, so first we can write this integration 0 to here L, because here our length of the box is L, psi star psi dx. So this is basically our common formula, that generalized formula, psi star psi dx divide dz is equal to 1. So here we know our psi n is this a sine n n pi x by L. So from here we can find out, or we can write here 0 to L psi star, so a square sine square n pi x divided by L dx is equal to 1. If we do this integration, sine square, we know that sine square x is equal to 1 minus cos of 2x by 2. So if we do this part simple integration, one can get it a square L by 2 is equal to 1, or we can write a is equal to 2 by L root square. So with this using this value a is equal to 2 by L, our psi n now becomes psi n is equal to 2 by L sine of n pi x by L. So this is the normalized, this is basically the normalized wave function of the particle. So we will plot that how, if it is psi is equal to 1, how this curve will change. So this we have shown it, that how we can find out that a value, and this sine square in pi x by L, this we can split it 1 minus cos of 2 pi nx by L divided by 2 by simple trigonometric formula is equal to 1, or we can write a square L by 2 is equal to 1. So this is our normalized wave function. And now suppose if we have that psi is equal this n equal to 1, so that means this is equal to psi 1 is equal to 2 by L, this is the constant term, sine pi x by L. So we can get a like that wave function when it will be psi 2, that is 2 by L sine of 2 pi x by L. So this factor is basically thus twice, so once we may have the positive and negative, so we can get a curve like that. So similarly for psi 3, psi 3 is equal to twice by L sine of 3 pi x by L. So basically it will be psi 1 complete and 1, so 2 will be in positive side, so here will be 1, it will be, so this is the wave pattern for psi 3 and so on. So now let us find out that in this potential box, how we'll find out the probability of finding the particle within the interval of some length. Let's give some example. First consider that calculate the permitted energy value of electron in a box, and that box width is 1 angstrom. So we know here it is written as an electron, so that means we know the m is the mass of electron. So mass of electron value, we know that this is nothing but is equal to 9.1 into 10 power of minus 31 kg, and the box with this given is 1 angstrom, that means L is equal to 1 angstrom, and this is nothing but 10 power of minus 10 meter, and have to find out the permitted energy level. So that means En we have to find out. This is the given in the example. So we from that one-dimensional particle in the box, we have seen that what is the energy equation, that En. So basically we know that En, this is basically n square h square divided by 8 m l square. So here basically this h is, we know the Planck's constant, so this is basically n square into 6.626 into 10 power of 30 minus 34 square, and then 8 into, here we have m value. So if we substitute all this value, one can get 9.1 into 10 power of minus 31 into L square. L is our 10 power of 10 square. So if you sorted it, the simplified it, we can get this equal to we can get 6 into 10 power of minus 18, and also we have this n square. So this is basically joule, or we can write it 30 approximately 38 n square ev. So this is our energy En. So now we know the minimum energy the electron can have is minimum state is will be n equal to 1. So that is, you can get E1. So that is basically 38 ev. And now the other energy value like E2, so this will equal to 4, because n is equal to 2, so 2 into 4 into E1, 4 into 38, 4 into E1. So this is approximately will be 152 electron volt. E3, we can calculate 9 E1, that means 342 ev, and we can calculate the so on like E4, En and all this. So with this formulas or particle in one dimensional bags, this solution wave function and energy equation, ones can easily find out the permitted energy levels. So yes, this is the which we have calculated just now. And now let us give that particle in one dimensional box, how we can find out the probability of finding the particle within that interval of, let's say, in this box. So let's try with another example, that a particle is moving in one dimensional box of finite height with this 10 angstrom. Calculate the probability of finding the particle within the interval of 1 angstrom at the center of box when it is the state of least energy. So we know from previous discussion that the wave function of the particle in ground state, at ground state, that means n equal to 1. This is the ground state. N equal to 1, that wave function, that will be obviously psi 1. So this is nothing but 2 root over 2 by L sine of n. We know the formula n pi x by L, so n is equal to here 1, so pi x by L. And the probability of finding the particle within an interval, we know the formula P is equal to psi 1 square, and this is nothing but we can find out easily from here, because here it is given that at the center of the box, that means if the box length is suppose this L, then center will be L by 2. So psi square x, this will be basically if we just square this one, we once can get twice by L sine of pi L by 2 over L this square. So this will be basically 2 by L sine square pi by 2. We know the sine 90 is equal to 1. So this term will be basically 1. So we can get 2 by L. So the probability of finding the particle within an interval of delta x at the center of the box is equal to, is nothing but we can say as psi 1 square into delta x. So that will be basically psi 1 square is value is 2 by L. So 2 by L into delta x. So here it is given in the problem, the example that with this 10 angstrom. So this means that delta x is equal to 10 power of minus 10 meter, and L is equal to, here it is given L is equal to here given 1 angstrom. With this given L, that means L is equal to this, yeah, L is equal to 10 angstrom. So we can write 10 into 10 power of 10 angstrom, and delta x basically this interval of delta x. So if we use this values in this above formula, then we can get W is equal to L 2 by L, that means 2 divided by 10 into 10 power of minus 10 multiply delta x is equal to 1 angstrom, that means this. So if we simplify this, we can get simply 0.2. So the probability of the finding the particle within an interval of 1 angstrom is nothing but this value, this. So now let's find out that how this expectation value of the momentum. So since here we have particle, we are considering in one dimensional box, let us find out that px. So calculate the expectation value. Let us take the example, calculate the expectation value of px of the momentum of a particle trapped in a one-dimensional box. So for finding this, we know that normalized wave function, let us see that what is the formula related to this expectation value p, so that we can easily find it. So let's start with the formula for px, that we know that expectation value of the px, that is nothing but px expectation value, this is the formula, is general formula minus infinity to. In our previous lecture we have find out that momentum in quantum mechanical operator or quantum mechanics, how we are defining. So that is basically the psi star expectation value will be psi star, then operator, and then psi dx. So here our momentum operator is minus I h by 2 pi d dx. So this is basically in 3 dimension minus I h by 2 pi delta, but here we are only considering px in 1 dimension, so it is by dx into psi dx. So basically the momentum operator P is basically, if we consider 3 dimension, it is nothing but I h by 2 pi into delta. So here what is our psi value in 1 dimensional box, that we know it, that in 1 dimensional that psi is basically psi n is equal to root over 2 by L sine of n pi x by L. So psi star also will be 2 by L sine of n pi x by L. So psi n is equal to psi n star. So now we can do from here that here it is d dx of psi. So that what is the d psi by dx? Let us find out first. That means 1 times derivative of this with respect to x. So it will be nothing but 2 by L. This term will be coming back n pi by L into sine, we know the derivative is cos n pi x by L. So now if we substitute this psi star value, this psi star value, this, and d psi by dx, this value, this, then we can substitute both the values, then one can get the formula like it, that minus I h by 2 pi and then 2 by L. So since it is 2 by L and 2 by L root over, so 2 by L is outside and outside is n pi by L, n pi by L, n pi by L, and integration is how here our 1 dimensional box we have assumed, or we have considered the 0 to L. So it will be, integration will be 0 to L and then sine of n pi x by L into cos of n pi x by L dx. So basically this sine pi x and this 0 to L sine n pi x by L and cos this integration is 0. So overall it will become is 0. So we can say that the expectation value of momentum of the particle is 0. Expectation value of the particle, expectation value of momentum px is 0. So now let us take that another one case, that what is the expectation value of position that trapped in this box L. So let us define this as, find the expectation value of x of the position of a particle trapped in a box L of void. So let us first define what is the expectation value formula. That expectation value x is written as, in general, minus infinity to plus infinity x psi square x psi square dx. So basically we already know the psi formula. Psi is basically 2 by L sine of n pi x by L. So if you square and then put in this equation, we can get it like 2 by L, and here the integration will be 0 to L, and then x sine square n by x by L into dx. So basically if we split it, this integration, we can get a bit bigger form, like you can get it x square by 4 minus x sine of 2 pi x n by L divided by 4 pi n by L minus, same will be for cos 2 pi n x by L under 8, then n pi divided by L square, 0 to L. So basically this two term with 0 to L, and this when it will be L, 2 pi n by L, and this will be 0 to L, this limit it will be 0, and this will be 0. So basically we will have this part only, 2 by L, and 1 is 0. For 0 it is 0, and for L it will be L square divided by 4, or we can write it is equal to 2 to L, L1 L, so basically L by 2. So this results that average expectation value x, that is basically L by 2. So this results mean that the average position of the particle in the middle of the box, that means average position of the particle is the middle of the box, because our box length is L, and here we have find out the expectation value of position, that is x is equal to L by 2. So that means the particle will be in the box will be most expected that average position of the particle will be at L by 2. That means the middle of the box or in the center of the box in all quantum state. So these are the various parameters with considering the particle in a one-dimensional box. So we have found it that the minimum energy of the electron that can have is of 38 electron volt in the ground state, and then we have also find out that particle in one-dimensional box, that the momentum expectation value of the momentum will be 0, and the expectation value of the position is at the center of the box. So basically the average position of the particle in middle of the box is the middle of the box in all quantum state. So now we will move on the one more application of Schrodinger equation in potential step. So basically in that potential step, here the potential will be bit stepwise. So before going to potential box, just three point in from this particle in a box. That particle in a box is quantum mechanical. It is very fundamental quantum model. So Schrodinger equations here gives the discrete wave function and energy, and this model illustrates key quantum concept, quantizations, boundary effect, and the wave behavior. So let us move for the potential step. That potential step here, let us consider the potential function of a potential step is defined by Vx is 0 at x less than 0, and V is equal to V naught x greater equal to 0. So let us first define that electrons of energy E move from left to right. From this the direction is from the left to right, that is along the positive direction of the x-axis. So it is desire to find the eigenfunction solutions of the time independent Schrodinger equation. So we have defined in this way that region 1 here the potential Vx is equal to 0, and in region 2 here this potential value is the V naught x greater equal to 0, and this black line is basically the potential, and this pink color, this is basically defining the real part of the wave function, and when E actually basically the less than the potential energy. So now let us find out the eigen function solution with considering this potential potential step with the time independent Schrodinger equation. So we know the time independent Schrodinger equation is d square psi divided by dx square. Here we are considering in one dimension, plus twice m h cut square. H cut is nothing but actually h by 2 pi, we are writing as h cut, and e minus v, and then psi is equal to 0. So this potential step, let us say as equation 1, this is say as equation 2. So now as we define in the this image, this region 1 and region 1 and region 2, that for region 1 here we have our Vx is equal to 0. So therefore this region 1, this Schrodinger equation can be write as this term is 0, this V is. So it will be basically the d square psi upon dx square plus twice m e by h cut square psi is equal to 0. So if we say that the this second order differential equation solution, so one can write the solution for this equation is basically psi 1 is equal to a e power of I some p constant p1 x by h cut plus b e power of minus I p1 x by h cut. So here a and b are basically the constant, and this p1 is basically we are writing twice me. We know that kinetic energy E is equal to half of mv square or p square by 2m. So now we have the scenario that some particle may be reflected by the potential barrier and some transmitted. So the first and second term respectively represent the incident and reflected particle. So the Schrodinger equation for region 2, that region 2 will be, here we have the potential V naught, so we can write the for region 2 the region 2 we can write the Schrodinger equation as d square psi divided by dx square plus twice m e upon h cut square into e minus v naught, because here our potential is v naught, psi is equal to 0. So let's say this is our equation of 5. So the solution of this equation 5, it will be looks like, let us say psi 2, that will be nothing but some constant c into e power of I p2 x by h cut plus d e power of minus I p2 x by h cut. So here this is, let's say, equation of 6. This p2 is basically here is in term, the energy we are writing in terms of p2, that is nothing but twice m e minus v naught, and c and d are the arbitrary constant. So now this equation 6, this first term, this is basically represent the transmitted wave. And the second term represent that wave coming from the infinity to the negative direction. So clearly that x is equal to x greater equal to 0, there is no particle can flow to the left, and d must be 0. So d obviously will be equal to 0. Therefore this equation 6 can be just this complete part, this part will be 0, and it can be written as psi 2 is equal to c e power of I p2 x by h cut. So the equation psi 2 will be c e power of I p2 x by h cut. This is our equation number 7. So we know the continuity equation of psi, that psi 1 and psi both will be, that psi 1 and psi both will be same at x is equal to 0, means when the x will be at 0 position, obviously this psi and psi 2 both are same. So we can, from if we apply this condition in solution of both the region, then one can get a plus b is equal to c, and this continuity of psi d psi by dx, that is that if psi 1 is equal to psi 2 is equal to 0, then continuity equation if we imply, that means d psi 1 by dx is equal to d psi 2 divided by dx at x is equal to 0. So we can write that let's say this is equation number 8, and we can write at p1 a minus b is equal to p2 c. So now if we solve this equation 8 and 9 for getting the value of a, b, c, and To simplify it, we can get like that. We can find out if we just solve it, this equation 8 and equation 9, we can get from here that B is equal to P1 minus P2 divided by P1 plus P2 A. Let's say this is 10, and we can get the C is equal to 2P1 divided by P1 plus P2 into A. P1 plus P2 into A. So this is our 11. So this is the, with considering that two wave functions, two different region, the potential step, the parameters A, B and C in terms of A. So now we have that in place of multiple constant, unknown constant, will have only one constant of A. So this B and this C basically represents the amplitude of reflected and transmitted beams in terms of the amplitude of the incident light. So basically this parameter B is for the reflected beams, and this C is basically transmitted beams of the in terms of the amplitude of the incident wave. So now if we define the reflectance and transmittance of the potential discontinuity, we can write in this way that reflectance R is basically the difference of magnitude difference of the reflected current with respect to the incident. So reflectance R basically is equal to the magnitude of reflected wave and divided by the magnitude of incident wave. And same way the transmission will be the transmission T, it will be the magnitude of the transmitted current. Here let's say this is not wave, reflected current, and this incident current, and this transmission is will be the magnitude of transmitted current. Divided by the magnitude of the incident current. So now the two cases will arise in our problem. That one first case is that E is energy that is greater than potential V naught, and second case is that E is less than V naught. So if we consider now the case 1, that E is greater equal to V naught, then basically when our energy is will be the greater than the potential V naught, then we can write P2 is equal to basically that P2, that term twice M E minus V naught. So this will be a real value. So now let's derive the expression for the current density in both region 1 and 2. So we know the uh, probability current J is basically H cut by 2 Im into psi star del psi minus psi del psi star. So now if we, this is the general formula for the current density, and now if we, since here we are considering the x direction, so our here this term will be in this way, that jx1 is equal to h cut by twice Im into psi 1 star d psi 1 by dx minus psi 1 d psi 1 star by dx. So if we use the solution of psi 1 value, and if we calculate this, if we use the psi 1 and here we just do the first derivative differentiation of this d psi 1 by dx and put these values, we can get this current density jx1. This can be find out as in terms of both the constant a and b with p1. So basically p1 by m, it will be basically a square minus b square. So this is, let's say, equation number of 30. So from this formula actually, or this relation, it is very evident that current in the region 1 is equal to the difference between two terms. So this is the current density. So current, we can say that this is A and this B. So it is basically difference between the two terms. So this first term is the proportional to the a square part, and a, this represent the, this part is represent for the incident wave, and the second term, which is proportional to b square. So basically this term is represent for due to the reflected. This is basically for the reflected wave. So now we can define as this potential, the probability current of incident, probability current of incident B. So let us suppose that probability current IP of incident beam. So this will be basically the a square p1 by m, and probability current for the reflected beam. So basically that if we say IR, that will be b square p1 by m. So this is the for case of region 1, and if we find out the current density in the region 2, so for using the for region 2, we can find out the current density Jx in region 2, that will be in terms of with the C. So it will be basically the C square divided by m into P2. So this representing, this term is basically representing the due to the transmitted current, or we can write this as IT. So this R basically the magnitude of the reflected current and magnitude of the incident current, and that transmit T basically the magnitude of the transmitted current and magnitude of the incident current. So one can formulate that T is equal to for P1 P2 divided by P1 plus P2 square. So this part is completely the transmitted magnitude of the transmitted current with respect to the incident current. So these are the, with considering the case 1, that is energy E is greater equal to V naught. So now let us look with the energy which is energy is less than in the case of, for second case, basically here that in the second case, the case 2, here basically the energy is basically E less than V naught. So when the energy is the V naught, then the that P2 value, so here basically that P2 root of this twice m, it is basically E minus V naught. This term will be imaginary. So now if it is imaginary, then P2 will be that, then we can write like P2 is equal to I root over of twice m E minus V naught, and that another P2 star, this will be minus I root over of twice m E minus V naught. So or this is equal to minus P2. So this, now if we want find out the probability current density, basically in this case E less than equal to V naught, then we can easily see that we know the current density formula. This Jx is equal to this is basically H cut by twice Im into psi 2 psi 2 star d psi 2 by divided by dx minus psi 2 d psi 2 by dx. So if we use this psi 1 psi 2 value and the psi 2 star, that one's easily can, with substituting this P2 star is equal to minus P2, we can find out that P2 star if we use is with is equal to P2, then we can get actually this Gx is equal to 0. So this means that the transmitted current is here, this IT is equal to 0. This means that magnitude of the transmitted current with respect to the magnitude of the incident current is 0, or we can say as the T is equal to 0. So by definition we know the reflectance plus transmittance R plus T, this is basically 1. So if we found it here T is equal to 0, then we can write here R is equal to 1. So this is the case for the one-dimensional potential step. The values or the or current densities or probability of current density with the transmitted and the reflected current with respect to both region 1 and region 2. So this is the potential step calculations. Thank you.